Now, let us look how can we calculate pH of solution of any chemical compound in water. When we say how we can calculate, we mean that we know acidity constants of these compounds, we know the formula and its properties, and our water is pure water. Next assumption, we are talking about so-called room temperature, somewhere between 20 and 25 degrees Celsius. Any other temperature will require different constants to calculate, otherwise the equations would be the same. Next point, what precision of our results we can expect? Very optimistically, you can calculate in some specific cases 2 digits after dot. So the results say 3.25 pH unit is possible. Less optimistic will be pH 3.3 for the same number. When you do calculations with modern computers, of course, you can easily get 6 digits or 8 digits as your calculation results. It's always wrong. Never go beyond 2 significant digits after dot. Calculations with higher precisions require knowledge of activity coefficients, require exact measurement of temperature, require complete absence of atmospheric impurities, and so on and so on. Never ever try to do such calculations unless you are professional in physical chemistry of solution. So let's start. First, let's look at our compound. Is it neutral, acidic, or basic? If this compound is neutral, so no part of this compound can produce protons or hydroxide, pH of its solution would be 7. Examples would be pH of ethanol, diluted solution is 7. pH of sodium chloride would be 7, and so on. Next, if our solutions are basic or acidic, we check concentration. If concentration of our compound is less than 10 to the negative 7 molar, pH again will be approximately 7. It comes from the fact that in pure water concentration of hydrogen ions and hydroxide ions are approximately 10 to the negative 7. In any other case, you need to do calculations. For the calculations, we are using these simple formulas coming from the fact that acidity constant and basicity constant of the same compound when multiplied produces ion product of water, H plus multiplied by OH minus, and it is equal to 10 to the negative 14 at room temperature. In other words, you can say that pKa plus pKb is 14, and pH plus pOH is 14. Now you can always convert Ka to pKa, going back and forth taking negative log, or 10 minus pKa will give you Ka. So if you have pKa, you can get Ka. If you have Ka, taking negative log gives you K. So let's look. If our compound is acid, first pH of this solution must be below 7. You're adding something acidic, you should have acidic pH. Next question. Is your acid strong or weak? If your acid is strong, then you can proceed and calculate pH by very simple formula, pH negative log of concentration. If your acid is weak, you need to solve quadratic equation, and solution will look like this formula. Next, from H+, you calculate pH. But in most cases, Ka multiplied by C is much larger than Ka squared. That means you can use simplified formula. pH is 1/2 of pKa minus 1/2 of decimal log of concentration. After you are done with your calculation, carefully look at your result. It should be less than 7. If a larger number is coming from very small concentrations, very close to 10 to the negative 7, it may be better way just to put 7 as your answer. Again, your answer never can be above 7. If you add acid, your solution is acidic. Next option, base. If you're adding base, your solution is basic, which means pH is higher than 7. Exactly the same as acid. We check if it is strong or weak base. If it is strong base, sodium hydroxide, for example, you quickly write the answer as pH equal 14 plus decimal log of concentration. If it is weak, you are solving quadratic equation, receiving this formula, you hook Kb and concentration here, and you're receiving concentration of hydroxide. From hydroxide concentration, you can calculate pH by this simple expression. pH equal to 14 plus decimal log of concentration of hydroxide ion. As with acid, in most cases, you can use simplified formulas. So we are given two formulas here. If you know pKb, you are using this one. If you know pKa, you are using this. Two more formulas. If you have mixture of acid and base, you are using Henderson-Hesselbach equation. Next, if your compound is amphiolite, so it can be acid and base same time, you are using H plus equal to square root of K1 multiplied by K2, or, which is the same, pH equal pK1 plus pK2 divided by 2. So this will be more acidic, this will be more basic constant. Of course, if you have amphiolite coming from polyprotic compound, you need to pick up proper pK1 and pK2 from the formula.